Actually, when Andy, who has to be at a meeting right now, I think he will come a little bit later, asked me to give this talk, I decided that I wanted to basically report what has been done here and the progress we have made here, and of course give an overview of where this whole business is hopefully headed. It's about bringing together two numerical methods, matrix product states and the dynamical mean field theory. And this is a topic that has been ongoing for quite some time, and I want you to walk through it from sort of like my perspective. I cannot talk about everything here. I hope it will be, of course, relatively technical, but I hope you see the physics that can be done with that. So before I get started, I just want to introduce the people involved. This is basically starting here, Claudius Hubig, a former PhD student of mine. He finished last fall. He's now doing his postdoc in the group of Ignacio Sirac at the MPQ in Garching. He's basically the guy who wrote all the codes. Then Niels Oliver Linden is the PhD student working on the actual DMFT-MPS relationship. And it was a great pleasure to start a collaboration here with Manuel Zingel. He's in the audience. Yes, thanks a lot. I think the project would not be where it is right now without the help of Manuel. And you will see that, I think, hopefully throughout the talk. And beyond the people that actually get the work done, there are, of course, all these people that have great ideas of what should be done, and that being Antoine, Andy, Olivier, and myself. Actually, the whole thing started with Olivier in 2005, sort of. And we are finally getting somewhere.
Well, we
got somewhere, you will see that. And so, without further ado, I want to get you started. Now, of course, in this audience, it's totally unnecessary to say much about the DMFT, so I will give you this 101 introduction slide, which you have certainly seen 1,000 times. You replace the interacting model by an interacting impurity, which is embedded in a non-interacting effective bath. The impurity dynamically exchanges electrons with the bath. And in order to make this problem sort of like to get it to a solution, you impose a self-consistency condition, which you may say is just that you say, well, there should be nothing special about the site or the cluster which you picked as an impurity. Well, it's slang somehow for this interacting cluster. Then the Green's functions and the self-energies of on the lattice locally should be the same as those of the impurity. In fact, this condition goes back a long time. It was Metzner, Vollhardt, and I think a few other people at the same time that saw that actually would give an exact solution of an interacting model, Hubbard model, in the limit of infinite coordination number or dimensions. And then it was basically Gabi, who is here in the audience, and Antoine, who turned that into a real computational method. There's this first review of modern physics from '96. And there's the second one from 2006. Several of the authors actually are in the audience. And the trend over the last years has been that you make DMFT more realistic, that you look at multiple bands, that you basically try to restore non-locality by looking at cluster methods, both in real space and in momentum space, that you look at materials, band structures by combining it with density functional theory. And there are certainly many other things which basically the experts are here in the audience, and I should not really say stupid things while they're sitting there. Okay, so what is it all about in this talk? It is all about the thing that we like to call the impurity solver, which is that at some point in the calculation, as you know, we have to calculate a Green's function. I write it in this rather vague way because depending on whether you do it on the imaginary time axis or on the real time axis or somewhere else, there are different prefactors, but ultimately it's about calculating the expectation value of this observable as a function of time. And the method that does this for this effective problem is the so-called impurity solver. And I would say it's quite fair to say that the key progress of the method has very often been related to progress in having better impurity solvers. And so you have those methods that are based on formulating the problem as an action. You had this good old Hirsch-Phi Monte Carlo, which is now obsolete, which was replaced by the continuous time quantum Monte Carlo method. Some of the inventors of that method are also currently in the room. Then there have also been methods which are based on formulating the problem via a Hamiltonian based on exact diagonalization on the numerical renormalization group. And then, of course, the question comes up, well, we have tried so many methods on that. Why shouldn't we try it with DMRG/matrix product states? A word on that. I mean, DMRG is density matrix renormalization group is what the old people like me say about the method. Nowadays, people will rather speak about matrix product states. What DMRG ultimately is a variational method in the state space of matrix product states. So basically, I will use that interchangeably. This was invented by Steve, who many of you, of course, know. He is visiting here regularly in '92. And if you want more details, I shamelessly point you to 2 reviews I wrote in 2005 and 2011. So now we have this question mark. And so why would you actually want to do that? I listed you several methods. Why do we need yet another one? You know, sort of like just to have another method and keep people busy. Now, the sales pitch is sort of like the following, that you say, well, all these other methods, and I just list these 3 here, CTQMC, ED, and NRG, they all have sort of strengths and weaknesses. And I'll just list the weaknesses because this is, of course, what you want to see. They say CTQMC, yeah, it's a great method, but you have to do an analytic continuation to real frequencies. And in certain setups, you have a sign problem, which you don't want. In exact diagonalization, you have the same issue because ED can only deal with baths that describe the Green's function on the imaginary axis. Otherwise, the baths would be too complicated because of the pole structure on the real axis. And this, of course, so you have the same problem. At the same time, small baths limit the realism of the method. Then the NRG is a wonderful method because it's right on the real frequency axis, but there is the issue that you discretize logarithmically around the Fermi energy. So what is going on there, you will have extremely well. What is happening further away from it is not so good. And then there's also the problem, if you look at multi-band, multi-patch problems, you will be looking at an exponential growth of resources, although there has been progress in alleviating that a little bit. But still, this is, I would say, the bottleneck of NRG. So the sales pitch now for DMRG is the following. Let's look at how the NRG people, for example, would treat this problem. They would ultimately look at a one-dimensional setup where you have the impurity on site 1, and then you have all these bath sites. There's local on-site energies, there's hopping going on. The details don't really matter here, but doesn't this look exactly like what DMRG is good at? It's a one-dimensional setup. Hey, we should do that. So, and what is it? You have no sign problem. DMRG doesn't have this notion of a sign problem. You would do it directly on the real frequency axis. There are techniques to calculate spectral functions on the real frequency axis. You can deal with much larger systems than ED, so you don't have this severe limitation. You don't necessarily have to do a logarithmic discretization. You're essentially very free to discretize how you want. Then if you look at multiband cluster methods, well, it will become more complicated, but there will not be an exponential growth in the complexity. And given that CTQMC has a hard time to get to really large beta, we go all the way. It's a calculation at beta equals infinity. So that's the sales pitch. And so I think it's a justified question. This has been going on since about 2004. Why is not everyone in this audience doing DMFT with DMRG and matrix product states these days? I mean, I think this is a valid question after looking at this list. So now is the hour of honesty. Let's see why this is. And I think there are 3 reasons why this business has been going so slow. The first is that I think in the first 10 years or so of that business, the problem was that the methods we had for calculating Green's functions were not really so good after all. I will briefly look at that, briefly look at the methods where you do it in frequency space, but this I will mainly do for completeness, because ultimately it turns out what you do is you have to calculate it in real time and then Fourier transform, and you will see why in a second. Okay, I think by now we have good methods to do that. And then the second stumbling block was that because, you know, the formalism looks so similar to what people would do in ED and NRG to combine it with DMFT, that there was a sort of like, and of course I have been involved in that, there was a sort of like an unthinking adaptation of what other methods do to deal with DMFT without really rethinking very carefully why they do it and whether there might be a totally other logic in DMRG. And I think this is something I will dwell on quite a bit in this talk, because this is sort of like technical stuff for DMRG experts. Here you really understand something more conceptual, which might be also valuable beyond the DMFT context. And I think now we are at the stage that we are really facing the real limitation of matrix product states, which is that they are giving a classical description of a quantum state, which is fundamentally not possible in a complex system because of quantum entanglement. And ultimately what we are dealing with nowadays is, can we overcome limitations of entanglement? And for those problems where we can, I think it is a wonderful method. I hope I will be able to show you this. In these other cases, we will probably be lost. And the question is, where will be the boundary? Yeah, that's something I will try to discuss in this talk. Okay, so a very brief look at what people...
Can you
Sure.
kindly explain that remark that it's intrinsically a classical adaptation?
Yeah, I mean, sort of like if you think just about the state of a spin chain of say L sites. Yeah, then the number of states that contribute to your state function is 2 to the power L for a spin 1/2, say. And so there is this exponential complexity in the description. What a matrix product state does is, if I find some chalk here, I mean, what the matrix product state does is it gives you a superposition of all the states. So like here in that case, say the spin states, all the spin up, spin down configurations, and then of course you have the scalar prefactor. But it represents the scalar prefactor by a product of matrices which carry as argument the local spin states. And then you trace this or do something like this. Now, the number of coefficients which you have in this ansatz is only polynomial. Say if you have a matrix of dimension m, then it would be m squared times L something. And this is sort of like, so by definition, in order to capture the full exponential complexity of the problem, the dimension of these matrices would itself have to become exponential.
So there's no notion of an RG a la, say, the Wilson solution?
Actually, there is.
Which is also not exponential, but gives me the right answer.
Yeah, there is some notion of that sort, but I think in the problems which we are discussing here, I think the more appropriate way is to think, because we don't have sort of like we don't have scaling properties like we have in RG.
You're not interested just in low energy properties, you're interested over a wide range.
No, I'm interested essentially only in the low energy properties. But the point is, sort of like, I don't think that the appropriate way is here really to think about it in terms of RG. Actually, this is an ongoing debate whether one should actually call it RG. Miles will probably confirm that Steve sees it differently. He thinks it should be called RG. There are ansatzes for DMRG which you can interpret exactly in the way of an RG flow. Yeah, but I don't think that this one here, where we are dealing with finite systems, which are not translationally invariant, which have hoppings of all sorts going on, that is the right way. The better way here to think about it is that the DMRG method is actually a variational method. And then what you're looking at here is at a restricted ansatz class, and the quantity which explains to you whether the ansatz is actually good or not is the amount of bipartite entanglement that is present in your quantum states. This is ultimately the best way of talking about it. I hope I will be able to show that to you as the talk goes on. So, anyways, anyone who wants to ask a question, please ask all the time. So what people did to do that, and this is how this whole business got started for DMFT, they would look at something, say, like the resolvent to determine the Green's function, and write it in the following way, that they interpret this entire object here as a state omega, and that state omega you can determine by solving this large sparse linear equation system. This is a very precise method, but it's really extremely slow. So this method has been brought to DMRG by Steve White in '99. In the DMFT context, the first people who really applied it seriously was Götz Ulrich and a few others. They solved the single band DMFT problem for the Hubbard model on the beta lattice admirably. But then already going to 2 bands, this is what Olivier and I really tried hard with this poor PhD student. I always say he got a great job afterwards, so we can feel relieved. Is that so far we got results, but we were not so happy about them, so the whole thing stayed unpublished. With hindsight, I think we should have published it. It was not so bad after all. But anyways, the big step forward came when, together with my colleague in Munich, Jan van Delft, we sort of like applied the Chebyshev expansion to matrix product states. This is relatively intricate in the details, but the fundamental idea is relatively simple. There are 2 versions of the algorithm. The one which we invented first, which was way too complicated. There is now a much simpler version of this algorithm, but this is just for people who want to implement something like this. To cut a long story short, you can determine a very precise spectral functions, and it's really extremely fast. So this is actually the method where we could first think about attacking this problem. I will not go into details because this is obsolete also for what we want to do. So just to show what Olivier and I then achieved, and it has to be said that in parallel the people in Graz, using exactly the same methodology, looked at very similar problems, both in the year 2014. What we looked at was a whole-doped Hubbard model on a 2-dimensional square lattice, represented paths on the real axis using a linear discretization. We determined the hoppings and the on-site energies exactly as NRG. People have been doing it all the time, just without the logarithmic discretization. And the reason why we chose that model was that there were extremely precise CTQMC results by Olivier, Gabi, and Antoine, and Michel Ferrero. I don't know the other guys so well, that had been produced, so we had something to compare against. Let's start on the right-hand side. So this was a 2-patch DCA calculation with 1 central patch on the Brillouin zone and then sort of like a boundary patch. And this is sort of like the central patch, this is the boundary patch, this is the Matsubara-Green's function. You see the agreement on the imaginary axis looks really good. At that time, we didn't worry too much about this deviation. Let's just say this can be sorted out and can be made to disappear. The really interesting thing for us was to go to compare what's going on the real axis, where we calculated all along and where the CTQMC people got by analytic continuation. And because you can really converge these MPS results very reliably, I think it's pretty clear and was accepted among all of us that sort of like this work, meaning the MPS calculation, that this is the actual result. And you have to see what it was probably Max Ent or Padé, what you did Padé at that time. That you see both have the same features, like also here pseudo gap, and you see here the feature that CTQMC has. It seems it's not as nice as the probably really correct feature. You have the same peaks. So you see the method is valid, and probably it's better than what can be done with CTQMC at that point on the real axis. On the imaginary axis, we do not really have an advantage. So the question is, why didn't everyone simply do time evolution and then Fourier transform? Because time evolution methods had been around for a long time. And the reason for that is that time evolution as such would not have been good enough. And but we knew how to do better, so we revisited this problem, and this is now the method that is used throughout, I think, by all the groups that are currently doing MPS plus DMFT are now using this method at one point or another, this so-called linear prediction method. And this I want to explain because you see a couple of weeks ago in this Quantum Cafe, we had a wonderful talk by, was it Martin Murigan? Is the name correct? Guys, you were there. Yeah.
Not there, but
he was there, exactly. And he had this wonderful experiments on one-dimensional spin chains at finite temperature. And some theoreticians had done extremely complicated Monte Carlo simulations. And after the talk, Miles, Steve, and I sat together and thought, okay, with this method, and DMRG, that would have been a much, much simpler and more accurate calculation. That's what we should sell to these people. And actually, that's what we are doing in some experimental collaborations just right now. So this method is useful far beyond the topic of this talk. Now, the problem of matrix product states is states of low entanglement, which obey the so-called area law, are very far and few in between in Hilbert space. Ground states belong to them, but the overwhelming majority of states does not obey the area law. If you look at the same system on a double the size, the entropy the entanglement will grow with volume, not the area. And if you do time evolution, you get out of that cozy corner of, say, a ground state or something like this. And what this means is that entanglement that can actually be shown is bounded by linear growth in time. In that case, which we are looking at here, it's better, it's only logarithmically growing in time, but still it's growing in time. And then there is a statement which you can more rigorous mathematically, but approximately you can take this home as a message, is the matrix dimensions you have to consider in matrix product states grow exponentially with the amount of entanglement. So this is an obvious killer. Long time evolution with matrix product states is simply not possible. Yeah, so which means that at a certain point in time, depends on the Hamiltonian, you simply have to cut off your calculation. And then you want to do the Fourier transformation. Of course, to do that, you have to dampen out that you suddenly run out of data. So you have to do lots of dampening, which of course corresponds after the Fourier transformation to an enormous broadening of the spectral functions. That's not nice at all what you get. So the question is, can we somehow, running out of the possibility to compute this stuff, can we guess the long time data and then Fourier transform without all sorts of dampening and broadening? And the ansatz which we use is incredibly stupid and simple. It just assumes that if you have a time series of data points xn, like n is a time index, for example, that you assume that the next point in time is simply a linear combination of, say, the last 10, 20 data points where the coefficients don't change over time. This is, of course, the big assumption, that they don't change over time. And how do you get those coefficients? I mean, let's make this ansatz. Perhaps it's a stupid ansatz, but let's make it. And if you make this ansatz, what you do, of course, is you take the stuff which you calculated, feed the ansatz into this formula into your real data, and determine the coefficients AI from that, from simply matching the data you calculated with your DMRG calculations. And once you have these coefficients, you use them to iteratively continue the time series from your last data which you had calculated, and in that way project you into the future. I mean, you can do that. The question is it any good? So just to show you how it works is, this was, of course, the simplest thing possible, the transverse Ising model. This is spin correlation in momentum space in time. For different k values, you have these curves. You can do that numerically. We broke off the numerical calculation at, say, time 10, used the data we had to predict the future, and because this is an exactly solvable problem, we could compare exact and predicted result, and you see that the prediction and the exact result sit exactly on top of each other, and this is the error. You see you're really talking about extremely small errors, and we could easily extend the time domain by a factor of 10 to 20 even, and get wonderfully precise line shapes. Now, this is of course so trivial as a model, so we also looked at many more complicated models. Just to give you one example from 2013, there have been more in between. Spin-ons in a spin 1/2 chain at finite temperature. There were nice experiments from Bella Lake in neutron scattering. And these are line shapes. So right cutting across here to higher energies. And as this is not the topic of the talk, let me just remark, as you can see, is that the DMRG data lie perfectly on top of the experimental data. So you have really the possibility with this methodology of this linear prediction to calculate spectral functions extremely precisely. The question is why? Okay, and the answer to this problem is the following. What you have is that if you do this linear prediction, what you actually do is you can work out this from the ansatz. What you're actually producing is a superposition of exponential oscillating decays, some formula of that form. And if you compare that, to a Green's function, look at that one and assume you have a single pole in the g of k of omega, then g of k in t by Fourier transforming back would correspond to exactly one term in this sum. So whenever you have a structure like that, where you have a few poles that determine an exponential decay, that ansatz should work perfectly well. Actually, the spin-ons where you have an entire cut, branch cut, is a very hard test case for this problem. So it's quite remarkable that it's working so well there. Here in our setup, which we will do later, namely imaginary time dynamical mean field theory, where at some point you have to calculate greater and lesser Green's functions like this object here, this is just a perfect setup, because this is exactly what the linear prediction will capture in the way it's set up. So keep that in mind, but it's a very useful method also otherwise. So we reran all our calculations. Exactly, it's the same results as before, the same curves, there's no way of distinguishing them. And the only thing that changed was that the calculation was about 10 times faster. And that was at a time when our ways of doing time evolution were much less evolved than nowadays. I would say nowadays a fair comparison would give about a factor of 100 or so in terms of speed. So really, if you want to get into that business, go onto the time domain, don't stay in the frequency domain. This is something which we did, which we could have done a few years earlier, but somehow no one did it. Except, of course, again, our colleagues in Graz, we had the similar ideas, I guess, the same time. Okay, so then let me go back to that. Then Olivier and I, and we were still nevertheless a little bit disappointed because, of course, we wanted to do really complicated things like bigger DCA clusters, multi-band and all that. And then, of course, we looked a little bit at the calculation times, and nevertheless, they were a bit disappointing. So what we did is we entirely revisited the methodology. So at that point, I would say we now know how to do Green's functions properly. There will be improvements which were achieved while I was here. I will show that later. But more or less, that's what we now know how to do. So what we next did is, and this was really the great idea of an extremely gifted PhD student I had, Alex Wolf, that we went back to look at the problem of the entanglement, which we just referred to previously. And before I go into that, I want to give you, without going in all the details of entanglement theory, try to give you some intuition about it from a very simple example. Namely, I want to look at a spin 1/2 Heisenberg ladder with an interladder coupling J. Along the leg it's 1. So this has to be mapped to a one-dimensional matrix product state geometry, and the question is how. So, and I want to discuss two approaches. The one is approach A, that you go zigzag. You interlace the blue and the orange. So your spin ladder turns into that object. Here you have the black interactions, which are next nearest neighbor then, and you have the interchain, which are the green ones here. You could, of course, also envisage doing something which is probably totally stupid, that you put one chain behind the other. Then, of course, you have short-range interactions here, but you have this enormous amount of interactions here. And the conventional wisdom in this business would be to say, well, all these spin interactions, they somehow propagate entanglement. They create entanglement. So if you do a bipartition here, you bipartite only a little bit, and here you cut a lot of interactions. So the approach B should be much, much worse than approach A when it comes to the entanglement present in this representation of the wave function. And indeed, if you do that, this is the entanglement in the approach A, and that's the entanglement in the approach B. And the fact that it's about 5 times higher, I mean 5, all this translates into exponential factors, it's enormous. In fact, this approach is so bad that you can't really even get it to converge properly. But now let's do something else. Let's make the interchain coupling extremely small, 0.01. Now the entire thing is reversed. Now the sequential approach, where you put one chain behind the other, is much better than this interlaced approach. And it's actually about a factor of 2 in between, if you look more closely, which means because of this exponential link that the dimension of your matrix product state should be squared in this sort of like verse approach, which is this interlaced approach. So can we understand this in the simple picture of drawing lines? Yes, you can, because if the J is so small, you can as well assume it's not there. Then in the interlacing approach, you cut 2 interactions. In the sequential approach, all this long-range stuff has gone away. You cut 1 interaction. So naively, you say, well, then it's probably doubly entangled. Well, it's exactly what you get. And, well, that's what you have. It's actually even correct. I mean, the really correct way of thinking of it, of course, would be the following. If they are essentially non-interacting, the ground state of the ladder is the tensor state of the 2 chains. And if you write that as a matrix product state in this dumb way, you're tensoring matrices, and this is how you get from the dimension m for a chain to m squared. That's the way you really would think about it. So let's apply this knowledge to the one-dimensional, or to the bath of DMFT. As you all know, that's the natural setup you would expect. The impurity, and then you have the non-interacting bath sites around it. You get this both in ED when you do a bath fitting a la Caffarel-Kraut, or if you do the bath discretization on the real axis, like NRG does it, or our DMFT, DMRG approach did it. So what you could do is you could do 2 things, among other things, is the one which we call the star geometry. Well, you don't see much of a star here, but what I think about it is like I step onto this object, which is a star, and I flatten it out. So you get these really long-ranged hopping terms. And then you would, of course, argue, well, I make this bipartition cut, that should be really strongly entangled. I mean, that's what I showed you in the last slides. You cut lots of these things and it's more strongly entangled. So, but what you also could do is what you have to do in NRG actually to get hold of your separation of energy scales is you do the tridiagonalization, then you obtain a chain where there's only nearest neighbor hoppings, which is nice from the MPS perspective because first of all, it's easier to implement short-range hoppings in the Hamiltonian operator, and that should be weakly entangled. So use this. This is what everyone had been doing. Okay, and then for whatever reason, perhaps I shouldn't say that by pure chance, we looked at that again, and we studied the single impurity Anderson model at half filling. So just to have a simple test case. This is the hybridization, semi-elliptical. Then this is what you would get from the for the couplings. If you do the star, you know, the flattened star, you get this kind of couplings. If you do the NRG-like chain mapping without logarithmic discretization, this is why they are not decaying rapidly. But you see they're all more or less of the same sort. So you would say, well, the reasoning should hold, which I gave previously. It's not that we have this 0.01 business that they are actually not existing. But what you find is, hang on. So what you find is, ignore the red dots, please, and just look at the green versus the blue curve. What we have here is the star where we actually put the impurity in the center. You have very little entanglement, and if you use the chain geometry where everyone would have said it's much, much better, the entanglement is much higher. And you see there's a huge factor in between here, which translates into a huge difference in the dimension of the matrix product states. And as calculations scale as the third power of this dimension, the computational gain by going from here to the green curve is absolutely enormous. And the reason behind that is actually relatively simple, because what you have to look at is not the couplings, but you have to look at the potentials. If you stay on the star, the potentials basically reflect the band, the energy of the band you couple to. If you do the mapping like you do it in NRG, what you get for half filling, for example, the potentials are all strictly zero. The important thing is that away from half filling, they are also more or less of the same order, whereas if you stay with the star, they spread a large range. And then you get something which people in quantum chemistry on DMRG in quantum chemistry had been exploiting for a long, long time. Because think about the impurity not being there, and you just fill up your bath with electrons. And then if you fill up this potential here, of course you fill all the states here with 2 electrons, and all the ones above here will stay totally empty. So you are looking at a product state which has 0 entanglement, and then you introduce the impurity which has this hopping and has this on-site interaction. That will create some entanglement, but mainly around where the Fermi edge is, which is exactly what you have here. If, however, you go to the chain, there's lots of hopping going on forth and back, which has nothing to do with the physics. It's not forbidden energetically because they're all half filled. And that's why basically you have this problem. And in fact, in quantum chemistry with DMRG, you have the same thing. You have the orbitals with high energy and with low energy, which basically do not participate at all. And the interactions do nothing but shuffle around stuff that's going on here. This is why sort of like everyone is now using this star geometry for doing such calculations in this business. Everything else will fail. The second thing we rethought, and this is where Andy got strongly involved, was where do we do the spectral function? Of course, you can also do it on the real axis, and at that point we were a bit daunted to continue on the real axis. The Graz people continued there, but that's probably a talk that Manuel should give to you, what the status on that is. I mean, there has been wonderful results, but it's also clear that if you try to do some more complicated problems, it will probably be pretty awful, despite the wonderful ideas they had. So we avoided all that and tried to do something simpler. We went to the imaginary axis. Why? Bath fitting on the imaginary axis is much simpler because there is less structure there. There is, if we do the time evolution in imaginary time, because this is basically a projection, there's essentially no entanglement growth in the time evolution, so we don't really have this usual problem. We would then expect that we can deal with a much larger number of patches and orbitals. The spectral function we could then obtain either by analytic continuation, or we could even try to look at the converged Bath Hamiltonian. The price to pay is, of course, that at that point, this is where we lose the information. On the imaginary axis, thermodynamics, that should do just fine. So the algorithm that results from that is effectively the same algorithm as people would do it that combine DMFT with ED. What you see up here, so I will not really focus on that, that's the typical simplest version of the DMFT equations. Then you have the Bath fitting, which you do for exact diagonalization. You get the hybridization function. You introduce a Bath with hopping terms and on-site energies that results in a hybridization function of that form, which you fit to that one in order to get hold of the hoppings and on-site energies. This is a standard procedure. And this is where we basically use the matrix product state technology, is to find the ground state, then to calculate the Green's functions, both in imaginary time and also in real time if desired, once we have converged the DMFT loop. So we did that. And in the first test, we went back to the old problem. The calculations became incredibly fast. We are talking about minutes for the entire DCA calculation, but you start seeing the price to pay. Real axis means what we had obtained previously by doing the DMFT on the real axis, which is the result which you basically should believe in. And this is what now happens if you go to the imaginary axis. And you see it's more or less the same structure, but you also see that you start missing out on features, like, for example, this feature here, where you have a vanishing spectral function at omega equals 0. And so this is the price to pay. If you look in more detail at the same problem, what you see is the advantage is you get away with much smaller baths, and you also see that it nicely converges towards the CTQMC result. But if you go onto the real axis, let me, for time reasons, just focus on the bad curves right here. You see you have all the structure. If you do a small broadening, for example, you have this peak here. You also have this shoulder here somehow. You have a dip in between, you have this structure here, so you say, well, maybe I shouldn't broaden that much. But if you don't do a broadening, you will still believe that you have two peaks here, where in fact you only have one. You simply do not really know what to do. Anyways, so like just to give you an idea what the problems of this method are. But what we then did is to move ahead to problems where sort of like not everything is already known from other methods. We looked at a 3-band Hubbard-Kanamori model for strontium vanadate on a beta lattice with a Hund's coupling, but not with a realistic band structure. That's what we did. I mean, I think most of you have seen that Hamiltonian already. This is what you typically have, the usual assumptions you make for the Hubbard-Kanamori model for a 3-band problem. Well, what comes out, let me just flash this to get to what I did here, is that, okay, there was extremely good CTQMC stuff by Philip, Werner, Andy was on that paper, Matthias and Emanuel, I think also. Were you on that paper? I think the CTQMC for strontium vanadate, I think you were. Anyways.
Well, this is the 3-orbital.
3-orbital.
It wasn't exactly strontium vanadate. It's just a semicircular density.
Exactly, that's what I just said. It's on the beta lattice. It's motivated by strontium vanadate. Yeah, absolutely. That's what I said about when I said exactly. But because this is actually one of the issues which we ran into, that here we got extremely good agreement, you know, by looking at the density as a function of the chemical potential. And to do something more complicated, we looked at the self-energy, where these guys had observed that the imaginary part of the self-energy has nice features because there is a phase transition from a Fermi liquid to a phase with localized with where magnetic moments are developed, which means that the self-energy at low frequency changes. I don't want to go into the physics at the moment, but what you can see is the dots are what they had found with CTQMC. This is what we get, these crosses, and you see when we make our baths larger, the agreement actually starts being very good. So we were quite happy at that time, but we wanted to push on and to do something which QMC had not done or maybe wasn't even able to do. I'm not so sure about it. I mean, methods make progress. So this is why it's as far as QMC went or potentially goes. So we went into something which at least at that time was totally unknown. We did a 3-band calculation with 2 DCA patches, so 6 correlated sites. And in fact, what you then observe is that the physics of the problem really changes. What we had previously in the simple 3-band calculation is that you had a large spectral weight at the Fermi energy, which now is replaced by a really huge gap opening here. And this is very, very robust under even very small bath sizes. It was not necessary to look at really large baths. This is a message which I think I can confirm from other stuff, which I'm not going to show, that in these multi-patch, multi-band problems, the larger they become, the smaller the baths are, you get away with reasonably, which is good. You see there's, of course, all this finite size structure going on. If you stay on the imaginary axis, you see that the Green's function already looks extremely converged, and you see a huge difference between the Green's function, which you get if you do not do DCA and if you do the 2-patch DCA. The physics changes drastically from the system being conducting to being insulating, and the reason for that is that probably the DMFT approximation was too strictly suppressing the interaction energy cost of hopping to neighboring sites, which of course technically is somehow in there, but it seems not to the necessary extent. So, and at that time we were extremely excited. We thought we could push forward a lot. So the first thing is we replaced, as Andy said, because he knows what was going on, we replaced the beta lattice by a real band structure for strontium vanadate. Technically it's all the same. It's just that the calculation time exploded. This is an observation which also I think our colleagues in Graz have made. If you have a model which looks more or less similar and you make it a bit more realistic and suddenly the calculation times explode. Honestly, we do not fully understand why. The second thing is we looked at a paper by Emanuel and Andy and others on multi-patch DCA calculations for the Hubbard model. you know, 1, 2, 4, 8, 16, the wonderful stuff you did. And sort of like we are currently doing the 8-patch calculation. And what happened is sometimes it converged very well, then some results didn't converge at all, and it was sort of like totally wild. We somehow had the feeling we don't have a really good control of the method at all. And so what we did at that point, and this is basically when I came here, because we really wasted perhaps a lot of time at looking at things which we really didn't fully control, we thought it would be good to go back basically to the drawing board and really study the method in full detail, what's going on. And I think I'm very happy I can say this after having been here for quite a lot of time, that I think we got hold of quite a lot of little stuff going on in the method, which now suddenly makes things converge very nicely, as you will see in a second. So what did we do? Did we look at strontium ruthenate? Well, this has been of considerable interest because it has lots of interesting theoretical aspects, superconductivity, Fermi liquid, Hund's metal. They're experimentally very pure samples. And for numerics, it's a very precise test case. If you kick out spin-orbit coupling, which this material has, because they're extremely precise DFT, DMFT results available that were obtained with CTQMC. I think this has been always a model that Antoine has been greatly in love with. The second thing is, however, that CTQMC faces a sign problem in the presence of spin-orbit coupling, which, however, is not a minor effect. This is DFT pictures which Manuel gave me. This is the Fermi surface without taking spin-orbit coupling into account, which is totally restructured around here as soon as you put in the spin-orbit coupling. So it would really be interesting to see the difference. This is the physics which we're actually aiming for, that we want to go to. So the program that we pursued here is in the knowledge that becoming realistic somehow made DMRG work much less good. I mean, the thing which we discovered for the pseudo-strontium vanadate and the real strontium vanadate, we thought we would go all the way right away, integrate our solver with tricks in order to access real DFT band structures, to really go all the way to kind of realism, and at the same time to be able to profit from all the years of development work that have been invested in tricks, in order not to reinvent the wheel for all these things that you can calculate there. I think the people here who are just working on tricks, they know what is possible there. So then in a first step, we wanted to have a high accuracy benchmarking and really understanding what our solver is doing. Then go back to the analytic continuation issue, and then do the off-diagonal bath hopping, which is what comes up in the spin-orbit case, and which is where the CTQMC starts developing its sign problem. And what we are currently playing with is a toy model where we artificially introduce the off-diagonal hopping that CTQMC hates, and see where we go, because spin-orbit coupling should not be fundamentally different at all. It's just that it loses us a good quantum number, which makes us all the calculation in DMRG slower, and you don't want to run tests on an extremely slow case. Unfortunately, I had hoped that by today I would be able to show you nice curves for that. I don't know, maybe tomorrow, but certainly not this afternoon. But I think we can already say a little bit where the whole thing is headed. Yeah. So what we do is we look at baths of 8 sites per band. So we have a 3 × 8 sites band. We fit I omega in an interval 0 to 6. We used, because this has been ongoing debate whether how you should weight the function of merit. Andy rolls his eyes. I see that. We do 1 over omega. Other people say it's just a factor of 1, which you should put there. In this case, it seemed, because Manuel tells me he has tried in other cases where it made a difference. In this case, it seems the 1 over omega seemed the best, but it didn't really make a large difference for the large baths, which we can relatively large bars, which you can use here. Something which I would like to mention is that we work at a fictitious beta equals 200, because this sometimes raises misconceptions. Our calculation is strictly at beta equals infinity. It's just to describe the continuous function, we have to somehow describe it by a finite amount of data, and this we do by sampling it at the points where the Matsubara frequencies for 200 would sit. As one can show actually from the calculations, if CTQMC pushes up the beta, it gets closer to our results, which really sit at beta equals infinity. In this application, we did not really learn much about that. All this worked nicely. Where we learned a lot, which I just want to mention for those people who are interested, you can always talk to me afterwards. What we realized is that all these problems we had with converging the ground state beforehand can be resolved by introducing additional quantum numbers into the problem, which take care of the fact that these, for example, the Hubbard-Kanamori model has terms where you hop electrons between bands, but only pairwise. And that means you do not access changes of particle numbers by 1 in your DMRG calculation. What we, as many other people, did previously was to introduce small artificial hoppings and then send them to 0, and this is really a nightmare. It's much better to basically enforce odd-even quantum numbers and then see where the actual ground state lies. Many of the issues we had in the stuff with the Hubbard model and the Van Date have totally disappeared now that has been introduced. So this was actually the first thing happened in the first days in February here. Then what we next turned to is calculating the Green's function. That turned out to be quite interesting, because there we learned a lot. Perhaps things which with hindsight should have been totally obvious. So the problem resolves at around a word where another guy, Olivier, is now rolling his eyes, tails. The large frequency tails of DMFT, Green's functions, that seems to be an ongoing topic over the years. No, it's being denied here. Yeah. Anyways, where does it come from? Well, it's the very fundamental thing that the anti-commutator and the definition of the Green's function with the time ordering conspire to have a jump of 1 at tau equals 0. And if you Fourier transform that, that will result into that for large frequencies, the Green's function should be exactly like 1 over I omega. And this is obviously a feature of small times because it comes for there. And this immediately presents a problem for DMRG time evolution because it's usually done in the form of time steppers. You calculate little time steps. So for example, if you calculate with a time stepper of delta tau is 0.1, what you get is that at these time steps you get the precise exact result. You definitely do. But in between, of course, you somehow interpolate, say linearly, like I show it here. And which means you miss out on all the short time details, which means while you get that roughly, you miss out on the 1. Yeah, you don't get exactly 1. In addition, you will have a large frequency feature simply from the Fourier transformation, which in this case would sit at 62.8. Okay, so what did we do to get around this? Actually, of course, we wanted to compare to something precise, which turned out quite interesting. What CTQMC does, and this is what you can see here, this is the imaginary part of the Green's function times omega, so that should go to 1 or minus 1 the way it was defined. This is what CTQMC produces. They get increasing amount of noise, and so what they have developed is a fitting procedure where they continue the tail. This is what you see here, the blue curve. Okay, if we do our time evolution just in the naive way, for the experts we use the TDVP2 method, which is here the fastest that we found. This is what we get, the green curve. That's not what you want. You really miss the 1. And if you continue to look at around this 62.8 where something should happen, you see that's what we get. That's where we should be. The blue curve, this is because Manuel did the calculations. This is where you should lie. And so what we then did is we used a method which does, the so-called Krylov method, which has finite time steps, but without any effort you can do whatever time steps you want to do, so you could really get the full infinitesimal small time behavior of the Green's function. To cut a long story short, if you do that properly, you get the dashed curve, and you don't see it because it's perfectly on top with the CTQMC curve. And given that there is no fit, no noise, I think it's a wonderful confirmation for your tail work in CTQMC, which seems to be exactly right. I think you should be happy about that curve, because we can totally rely on this, the dotted curve. And in fact, from the way we do it, you get some artifacts at around I omega 62 or something, which however are totally irrelevant for whatever fitting you are doing. I can explain this more detail, but there's no need, I think, to do that because I'm running out of time. So why actually do we care about that? Because you could argue, well, these guys are fitting in the interval 0 to 6 and only. Why do they care about stuff going on at 30, 40, 50? The second thing is, we in DMRG can calculate densities directly. We don't have to Fourier transform our Green's function at tau equals 0 plus or 0 minus, which means you would have to have the large frequencies correct. So in some sense, we could say from this perspective, doesn't really matter. The problem, however, is that the self-energy will become totally wrong. And then we have a problem with tricks. That's actually what got us into the whole thing, because you see, if you look at the Dyson equation, the wrong prefactor of G, which is not exactly 1, whereas here it is exactly 1, will give you something which is linear in omega at large frequencies. And that's what you get. Now, actually the deviation already starts at relatively small self-energies. So now, having worked all that out, we can finally turn to the results. CTQMC was done at beta equals 400, really. We did it at infinity, but sampled at beta equals 200, which has the nice advantage that the data points interlace, and you can more nicely see how they sit on top of each other. What you observe is the agreement on the real axis is very good, but not optimal. This has probably to do with some stuff we did to the chemical potential. If we look at the imaginary part, you see the agreement between the CTQMC calculation and the MPS calculation is absolutely very good. And if you do a harder test by looking at the self-energy, what you see is, here you don't actually even see the deviation between the MPS and the CTQMC result. There are 2 lines because there are there's 1 band and 2 degenerate bands in this problem, so you expect 2 lines for the self-energy. If you zoom in, you see the agreement on the self-energy is now, I would say, more or less perfect. In particular, also at the low frequencies, which we are, of course, particularly interested in. So I think on the imaginary axis, everything is absolutely doing fine. So the question is, of course, not what do we get on the real axis. I mean, from here, it's clear what happens. We can do all the usual calculations, which you do with imaginary time Green's functions. We could look at phase diagrams and that sort of stuff. But what happens if we go to the real axis? Because it might be that there's, of course, some structure hidden in here, which you do not really see with the naked eye, but which analytic continuation methods will pick on and give you a totally different result. And that's actually not the case. So let me go to this right away. Padé gave bad results all the way, but Max-End was the method to use here. For Max-End applied to matrix product state results, because they are noise-free, you have to introduce some artificial noise. The noise which Manuel introduced, because this was his work, which Manuel introduced were actually of the same order that the noise of the CTQMC results was. And then that's what you get. I mean, this is a larger picture of the 2 bands, and this is zooming in at the small frequencies. And we would say that the agreement is about as good as you could possibly expect. Olivier, your comment?
No comment.
No? No comment. Okay, so that's where we stand. So basically, this is a valid method which produces the same results and is now totally stable. What I would like to revisit very briefly is just I have a few more slides, but I will go through that very quickly. We tried to improve on the technique to do a direct calculation in real time, because at the end of the DMFT calculation, we have a converged Hamiltonian. And then of course we can calculate a Green's function in real time, do this linear prediction thingy, and then afterwards do a Fourier transform. Now the problem is that long times is of course not really possible for us, and we have to rely that this linear prediction actually works. So in some sense it's a bug. But in fact, it's not a bug, but it's a feature, because what would happen if you really look at the long times? At long times, the Green's function will resolve the fact that your bath is very finite. And so what you do, all the numerical effort which you invest, which actually explodes exponentially if you look how long you take to get that far with your Green's function, all this stuff here which you calculate at enormous numerical expense is only finite size effects. So what you really would want to do is you only look at the short time evolution, whatever that means. That sees the bath as if it were describing a thermodynamic limit system. Do linear prediction only from the stuff at the beginning. This is actually what gives you that curve here. And then you do the Fourier transformation without any broadening or anything to get rid of finite size effects. You don't need that. And that this is kind of a meaningful approach you can see by comparing what the real-time evolution for the various Green's functions gives with DMRG, which is certainly very reliable. All these wiggles, and that's what you get if you take the spectral function and retransform back to a Green's function g of t. At the beginning, as you can see here from the enlarged portions of the diagrams, at the beginning they agree extremely well, then they start deviating, and back there it's certainly only finite size stuff. The problem, of course, is, and this is where the disappointment with this approach essentially rests, to cut a long story short, is whom do we believe at intermediate times? Where do the finite size effects really start? Or where is an effect which simply Max End has smeared out, but which is really there? We don't know. Here you can see some of the efforts which we made. I will get across the slide, just show you what we have finally. This is about the best what you can get. This is the spectral function for one of the bands, the XY band, the prediction being made from relatively short time. CTQMC would be the dark blue curve from Max End. And this is what we get with various broadenings. You see the broadening doesn't really have a big effect at all. This shows that you're really dealing with the thermodynamic limit information. But what you also see is, well, you have the flank here correctly, but you get the peak wrong. Of course, we do not really know how precise the peak really is. It's all this sort of problem. You have additional structure here, which probably is not physical. Perhaps it is. We have all these issues. So I would say the problem of the analytic continuation rests as unsolved as it has been all the time. So to finish this off, let me just mention that we had done relatively complicated calculations. Well, they were fast in the sense that a typical loop time for this problem was 4 hours or something like this. And to become faster, of course, you can do things like do a shorter time evolution that gets you a factor of 2 and do all sorts of things. So we can probably speed up the typical DMFT loop in this problem to 1 hour or so without any real effort. But we also tried, and that was interesting, is to reduce the bath size. Because once the bath is very small, you wonder, why don't you do ED all along? And what you see is baths with L equals 4 really give strong deviations for the Green's function, in particular for the real part, but also for the imaginary part. L equals to 6 and L equals to 8 baths on the imaginary axis seem to be about as good as L equals 8. The real problem starts if you go to the real frequency axis, where we did sort of like Max End on MPS results, or Manuel did. This is sort of like the blue curve is CTQMC and NPS in very good agreement, and that's what you get if you do the shorter bath. and then you see you get a nasty double peak structure, which certainly isn't there physically. So what you have to do is you have to realize that this is a system with more finite size effects. So what you do is you increase the amount of noise you introduce, like from 1 to the 10 to the minus 4 to 5, 10 to the minus 4, then the structure starts getting nicer. But what you can see is at that time it's turning into total black magic. So probably the bath size 8, which agrees extremely well with CTQMC, is the thing to do. Now, on the last slides, 2, and then I'm done, is what happens if we become off-diagonal, which is, for example, done by spin-orbit coupling. There's, from Eva Pavarini and others, there is this sort of like hopping matrix, which I will not explain, but as you see, it's off-diagonal a lot with all these imaginary hoppings. And so the fitting is now one of a hybridization matrix valued function. You have not just hoppings from the impurity to its bath, but from one impurity to a bath and back to another impurity. So there's many, many more hopping terms, many more fitting parameters, and the resulting Hamiltonian, which we have to deal with, becomes much more complicated, and potentially we lose the U1 symmetry. So that's the challenge we are currently facing and working on these days. What I can say from the tests we have made so far is that surprisingly, because we had thought that the bath fitting procedure with these many fitting parameters would be the real problem, for the time being it seems that this is working, because this is a bit in the unexplored regime. Because you use the usual kind of minimization routines, and suddenly you have 60, 70, 80 parameters. Could this work well? It seems to work well. On the other hand, in the resulting Hamiltonians, at the moment, we have indications for a strong growth of entanglement. In fact, this is something which I think we have an idea of how to deal with this if it's borne out by further calculations, because we had already seen all that in the 3-band vanadate or pseudo-vanadate with a 2-patch DCA calculation, because a real space cluster and a momentum space cluster, as in DCA, they are related by a discrete Fourier transform. And if you do that, what you find in that problem is, if you have the cluster in momentum space, like DCA, the bath is diagonal, but of course the on-site U becomes non-diagonal. If you do a real space cluster, then of course 2 impurities where the electron can hop away from and back to the other one, so the baths become immediately off-diagonal, but the on-site interaction U is diagonal. The question is, what do you do? Of the many versions you could do in between. And there it is, like CTQMC doesn't want the momentum space cluster because it has a sign problem. It prefers the momentum space cluster, it doesn't like the real space cluster, sorry, because there it has a sign problem because of the off-diagonal hopping. On the other hand, we found already at that time that the matrix product state has a very clear preference for the real space cluster. And that's surprising, because you would have thought that with these many off-diagonal hoppings, the entanglement might be much stronger in that case than in the other one. That's what I would have bet on if you had asked me to place $10. It turns out that, again, it's like with this star chain geometry. It's quite counterintuitive that for whatever reason, the MPS calculation likes the off-diagonal hoppings. At least it liked it in those cases. But you see there's an enormous amount of stuff we can play with to try to alleviate the problem of entanglement once we have these off-diagonal hoppings. What really frightens me more, which for the time being seems to be harmless, is this off-diagonal bath fitting. Yeah. Okay, and this brings me to the last slide, which is, I think you can read yourself. I hope you have seen that this ongoing struggle of marrying MPS and DMFT is producing some results after all, that we are now at the stage that I think we really understand each detail of the method reasonably well and can reproduce state-of-the-art CTQMC calculations really in great detail. And what I would like to understand in the next few weeks, months, of course, together with my PhD students and with Manuel and the others that are interested in that, is how well we will be able to deal with that, because that would definitely take us way beyond what CTQMC can do these days, and that then would have made this day, I think, extremely valuable. Thank you very much.
questions?
Exactly.
So, I mean, naively, I would have thought that this kind of problems is naturally amenable for infinite MPS, right? Because you have a buff or some, let's say, something which is natural in the thermodynamic limit. Is it possible to use IMPS in this case? Or,
Well, in this, sort of like in the framework of the DMFT with a kind of an effective bath, it's not, because sort of like you lose the simple property that all these hoppings and on-site energies, they are all different. So you are, how should I say, arbitrarily far from the notion of a translationally invariant system. Of course, you could think about doing something with IMPS, but then that would rather take you back to dealing with the full problem, and you would set up a totally different framework than the DMFT one.
Wait, so Emmanuel on the back?
Yeah, so when you're doing your off-diagonal hybridization fitting, you were mentioning that you can find a basis where your hybridization is almost diagonal or diagonal enough that the fitting becomes simple. So
This was, sorry, no, this was the case. This is not, this is a very good question, because no way of getting rid of that. What it might be possible to do is, of course, to do the fitting in whatever way you want and then rotate to other orbitals where the entanglement is lower. This is a degree of freedom which we should fully exploit. And this is why I brought the third problem where we had already played with that, was this pseudo-vanadate on a beta lattice, the Hubbard-Kanamori model, like referring to this three-band problem with the two-patch DCA, where actually you had the choice of going between real and momentum space as the simplest transformation. You could do more, where you have the two extreme cases, it being very off-diagonal, and CTQMC hates it, and MPS loves it, and the other way around. And this is, of course, what inspires us in playing very freely. For example, in this paper of 2015, we did the fitting in the diagonal representation to keep the fitting simple. And in order to do the MPS calculation, we rotated it to be off diagonal, did all the calculations, and then we rotated back. And that worked wonderfully well. So there is a degree of freedom which we have not really started exploiting yet in that business. But this will really, I think, be a core to get the whole thing work reliably.
So I had a question about, you showed results calculated in real time and you compared them to analytically continued results. I think mainly to bring out the differences you saw between them, but can they be like blended together? Can you use the real-time results somewhat to constrain the rotation and try to give a better prior for it in an accent or something?
That's something which we have sort of like rumored about doing, which we haven't done yet, because actually sort of like, I mean, you know, finite manpower and all these sort of things, but it's true. I mean, sort of like probably the results we get from the analytic continuation by real-time evolution, well, pseudo-analytic continuation, are probably, they are bad in some sense, but they're good enough to provide at least some structure which is better than a prior which is just flat. Yeah, in that sense it would certainly be worthwhile to see what does it do to the analytic continuation we do with the raw data G of I omega. We simply didn't have time to explore that yet. It's on the to-do list if we find the time. I would be very interested.
Ready?
Yeah, I was slightly confused by this 1/omega mild controversy or whatever. Isn't that analytically computable? Just given the microscopic model, the high frequency 1/omega, that's the leading term.
No, the only question is how you impose that a priori known information into the calculation to make a sensible approximation.
That's, I cannot phrase it better. I mean, we know that has to come out, but the computer refuses to produce it. That's the sort of thing.
Isn't that a question of, okay, so if you have data that's sort of doing this, right, and you know that, assuming there are no bugs, that it has to be matching to a 1/omega, isn't that a question of post-processing somehow of the data rather than computation?
Well, actually, it's too wrong to allow simple post-processing because Olivier and I mean, perhaps hadn't we played with this problem already many years ago when you tried to somehow impose it? But yeah, we had. Honestly, I've forgotten what we did, but somehow it didn't really work out. That's the answer I have to give. It's almost 10 years ago when we tried that, and sort of like the direct calculation, which with a proper time evolution algorithm, which we have available anyway, so it's no intellectual challenge somehow because we have that thing, does it for us. What one could of course do is, there are commutators, which, I mean, where's Hugo? Hugo and others. I think Hugo Lode was also on the paper, and I don't know whether you were the first, other people that did it before you. I mean, there are commutators which you can calculate, which do not just give you the 1 over omega tail, but also the 1 over omega squared and so on and so forth correction. The reason why we don't do that, we could actually probably calculate these commutators very easily with DMRG, is that as we are doing the fitting, in the sort of like low frequency regime, we do not really have at the moment such a big interest in determining this more precisely. If need arises, we can do that. So far, it was simply not necessary.
But don't forget your post-processing has to take a model which is violating the fermion commutation relation and turn it into one that does. That's why it's not a trivial post-processing issue. Because that one is really a statement of the fermion commutation, anti-commutation relations.
But the models that are trying to solve do not violate fermion.
Correct, but the point is if you have answers which
that
are not decaying as 1 over omega, but some other
I thought the
component.
issue was that they're decaying, but they have.
No, the coefficient of 1 over omega is wrong. The coefficient
So
has
what
to
we
be
have,
precisely 1.
so what we have is
commutation.
alpha over 1 over I omega, and the point is if the alpha is not strictly 1, we have violated the anti-commutator, and this is probably something which you would not want to have.
But
Where
is
does
that
it?
the case?
Yep.
Why?
Why? Because because you have a method which calculates everything very precisely, but as I showed, sort of like you have this Green's function which looks like this, but if your algorithm kicks you out these precise values at discrete points, to an accuracy whatever, 10 to the minus 7, 10 to minus 8. What you have never seen in CTQMC in that quality, but it doesn't really help because what you have is, let me draw this exaggeratedly, what you do is then you have to interpolate between here and there, and what do you do there? Yeah, and sort of like, and so you can do some weird Simpson stuff that gives you totally ridiculous results. You can be honest and say, I just do it linearly. It gets.
Yeah. Sorry, but why not just multiply it by omega and subtract the exact number? I mean, that's a check, right? That should
maybe we can discuss this offline because this is getting technical. So there are other questions? Yes.
So I didn't quite understand why you needed maxent at all in your way of doing things. I thought you did the entire calculation in imaginary time.
Yeah.
You get a Hamiltonian, and now you can evolve the Hamiltonian in real time.
Yeah, but this
So
is
exactly.
this is exactly because that's what we thought. That sort of like, well, maybe it's good enough to have this Hamiltonian, which we can do real time and so forth. And from what I showed, what you see is you have to sort of like really be very good at picking the short time window from which you then try to extrapolate the results and do the Fourier transform. And it turns out at the moment the best answer I know is that this linear prediction gives you back how good it was at fitting the raw data. And the better it was able to fit the raw data, the less artifacts you seem to have. But it's really black magic. It's about as bad as choosing these sigmas and the priors in the max end. So that is why at the moment I would take the conservative approach and say, let's do max end with some noise because we know a bit about max end or other people know about it, and rather not look into this real-time evolution much more at the time being, pending a great idea that I haven't had.
Okay, so on that note, why don't we thank Uli again?